Hello, y'all. Barely Berry Jr. here, doing some astronomy, astrophysics, doing some reading today. I had mentioned that I would make a video about some of my research soon. What I'll do is do a a literature review, reading an article on what's been previously done on the things I'll be forwarding. So this is an article that is written by the professor, the advisor I'll be working with, Dr. Keel, and a previous grad student at SMU, Dr. Dungana. So the idea is right now I'm getting a better understanding of variable stars and stars in general, modeling stars that'll help me in my future research with likely dealing with supernovas, where I can take a supernova and look at not only the light that's emitting from the supernova, but also the velocity at which the mass of the supernova is expanding, and using these things, the apparent luminosity, the actual luminosity, and some detailed analysis to determine the distance of the supernova away from us. So there's actually some interesting physics that we'll see how much this paper goes into it. It's a 18-page paper. Of course, a lot of that will be references. It's like almost a page of references. So I'll see how far I get. I'll stay here for about an hour and a half, and I may be back later to do some um, problem solving. All right. So we have cosmological distance measurement of 12 nearby supernovae, 2P. So type 2P supernova with ROTC 3B. And ROTC is a telescope that my understanding was built by the folks at SMU. And you can see the SMU folk, so leading the paper, Dungana, Keel, Staten, Vinko. If I remember right, he was at SMU, is at UT at the time. So two of my current school and my alma mater are the lead authors on the paper. McDonald Observatory at UT Michigan, University of Michigan is involved. San Diego University of Tokyo person is involved. University of California, Berkeley. Of course, now a lot of things are collaborations between groups and people. So we present cosmological analysis of 12 nearby Z. That's the redshift, how far away it is. Type 2P supernova, SNE 2P, observed with the ROTC 3B telescope. To achieve precise photometry, we present a new image differencing technique that is implemented for the first time on the ROTC supernova photometry pipeline. With this method, we find up to a 20% increase in the detection efficiency and significant reduction in residual RMS scatter. I need to learn what RMS scatter is. Let me make a note of this. Right now, this is note which paper we're reading. So 12 nearby, Z less than 0.06. Type 2P supernova with ROTC. That's basically a proprietary telescope and a new technique was utilized, which is all interesting. And welcome those who show up or watch. I am watching the chat, so just you can drop a line. I should be able to reply immediately. Well, the SN light curves when compared to the previous pipeline performance. And it's like you can see my highlights. We used the published optical spectra. So maybe I'll just highlight in the paper. That works. Yep. Looks like that's good. That make it color. RMS scatter. So I need to learn what that is. The supernova curves when compared to previous pipeline performance. We used the published optical spectra and broadband photometry of well-studied type 2P supernova to establish temporal models for ejector velocity. This is basically the stuff of the supernova, the matter, mass of it, how fast it's expanding, and photospheric temperature evolution for our type 2P population, right? Oh, it duplicates when you copy over. I thought it would like merge. This study used measurements that are competitive with other methods, even when the data are limited to a single epoch during the photospheric phase of supernova 2Ps. Using the fully reduced Razi photometry and optical spectra, we apply these models to the respective photometric epochs for each supernova in the Razi 2P sample. Like I feel like I need to look up Razi. I'll look that up real fast. So do I remember this page? So let me share this really fast. See how that looks. Okay. So this is the Razi page, the Razi telescope. See a little bit about Razi as well. The primary goal of the Razi project is to achieve observations in optical light of gamma ray bursts. To carry out our program, the small but powerful Razi telescopes operate at sites around the world. Explore Razi operations, discoveries, and research pages. About the robotic optical transient search experiment consists of two phases, Razi 2 and Razi 1 and Razi 3. Razi 2 was an abortive intermediary phase between the two. Razi 1 consisted of 4 mounted CCD cameras. Razi telescopes operate at sites around the world. Razi 3 consists of 4 0.5 robotic test-grain telescopes managed by a fully automated system of interacting daemons within a Linux environment. The telescope has an F ratio of 1.9 using a field of view of 1.85 or 1.85 degrees. Right, looks like the picture is down. We've written a comprehensive technical description of Razi 3 system published in the PASP journal. You can retrieve a PDF version of the paper here, so I'll make sure to do that. I'll talk about the telescope a bit. So open up well. Yeah. Okay. Interesting. All right. So this is the telescope that collected the data. You can see how light is coming in, bouncing off mirrors, then passing through several filters or bands, then hitting a CCD. So looking at the images there. So it seems like a pretty advanced telescope. Here's the Rothsey in Australia. Rothsey 3 mountain in Australia. Wow. They say it around the world. All right. So I have to take a look at this. Here's my advisor here, Dr. Keo. All right. So that's pretty cool. Let's go back to that doesn't mean have to take some time another time and look at the Rothsey stuff. Back, so we're going back here. Using fully reduced Rothsey models, Rothsey 3 sample. This facilitates the use of the expanding photosphere method to obtain distance estimates to their respective host galaxies. We then perform cosmological parameter fitting using these expanding photosphere method distances, from which we measure the Hubble constant to be 72.9 plus 5.7 minus 4.3 kilometers per second per megaparsec, which is consistent with the standard lambda cold dark matter model value derived using other independent techniques. So the idea is that even though they're using a totally different method, using different data, utilizing a different means as far as supernovas rather than variable stars. And again, if you have any questions, let me know in the live chat or the comments. I'll try to answer as best I can. We can see that they're still getting a comparable result. But the idea is that my cohort will improve upon the results they did to see if we can get a even better result and try to ultimately constrain the Hubble constant. Introduction. Supernova cosmology has been toured over the past few decades. Let me see about fitting this in the window a little bit better. Supernova cosmology has matured over the past few decades. Supernovae have proven to be excellent distance indicators for astronomy and cosmology due to their enormous and standardizable intrinsic brightness. Specifically, the improvements in the methods to precisely calibrate distances using the luminosities of supernova type 1a remain in the forefront of supernova cosmology. Okay? With the arrival of deeper surveys, these methods are being tested at even higher redshifts and will prove complementary to other high redshift cosmological probes such as baryon acoustic oscillations. So that's an interesting thing. My understanding is that in the expansion of the universe, there's, I guess you could say, shock waves that sort of reverberated through the matter of the universe, and galaxies form on the edges of these shock waves, I guess you can say. So there's galaxies don't just form randomly; they form, I guess you could say, at the edge of this pressure wave. Is my understanding, which is a very rudimentary understanding, but that's the idea. Cosmic microwave background, that's the actual remnant of the thermal energy from the actual Big Bang itself, has been stepping down in frequency over the millennia, and now it's down to the microwave range. I think it's about 2.7 Kelvin as far as temperature. and weak lensing, which is going to be gravitational lensing. While supernova type 1a yield remarkable precision for the distance calibration based on their peak luminosity and light curve width relation. And Perlmutter and his group is one of the people that got a Nobel Prize for that. Pretty sure they learned, if I recall properly, that the universe is accelerating in expansion utilizing supernova. That's when back when CCDs first came out. There remains questions about the potential impact of discrepancies between the supernova type 1a models and the actual physical processes occurring. Supernova 2P are continuously gaining interest as a standardizable candle population that provides a potent alternative class of distance indicators. The supernova 2P are believed to arise from the catastrophic, here we go. The supernova 2P are believed to arise from the catastrophic gravitational collapse of the iron core of massive stars that have retained a substantial hydrogen envelope even at the time of collapse. And we have okay, we could stop there. I was about to highlight some of the background, but we'll just focus on the type 2P. Because the explosion mechanism as well as the radiative transfer of 2Ps are believed to be better understood than 1As, the distance estimation is expected to be less affected by the systematic uncertainties due to explosion physics. While supernova 1As may exhibit higher absolute luminosity, supernova 2P explosions also offer tremendous luminosity and occur more frequently than type 1A. So my understanding about type 1A is that a neutron star, a white dwarf star really, reaches the mass of about 1.3 solar masses. And my advisor was explaining that to me yesterday or the other day. Basically, as the mass increases, the pressure on the matter in the star increases, which starts to force the atom smaller and force the electron closer to the nucleus of the atom. And there's always a slight probability that the electron will be in the nucleus is very small, but as the atom is compressed, that probability increases. And at a certain point, that probability reaches a threshold where the electron does appear in the nucleus. And when the electron and the proton touch, they form a neutron, and all the space that was occupied by the electron being spread out in their probability distribution around the nucleus, that space is now free, which allows a greater collapse. And that collapse then forces other electrons close and join in the nucleus, and they further collapse, and it ends up being a runaway process, which causes the star to heat up as it's collapsing. Things are getting closer together, and then there's a runaway explosion at a certain point. The difficulty is that, and that's why they mentioned, where was it? Explosion mechanics. So the explosion mechanics, because let's say the composition of two type 1A stars are slightly different. Well, like for instance, a heavier star may explode at a lower mass, like a star with heavier matter in it. Might explode at lower mass, perhaps because it's already so dense already. And so that will, change the light curve because the mass will be different, the matter is different, so the light curve will be different. So these are some of the uncertainties, systemic uncertainties due to type 1As that he's speaking of. While 1As may exhibit high absolute luminosity, type 2P explosions also offer tremendous luminosity and occur more frequently than 1As, presenting themselves as competitive distance indicators over an extensive redshift baseline. While these supernovas show substantial diversity in their photometric and spectroscopic properties, strong correlations in photometric and spectroscopic observables during the recombination phase can be exploited to provide a distance calibration. Okay, I have to look at that one more later. Several methods have been proposed over the last few decades to make the 2P distance measurements calibratable. These methods are generally driven by the correlations of the luminosity with the expansion velocities. That's what I was mentioning earlier. Correlations of luminosity with expansion velocities. The pioneering work of Christian Kwan, while back in 1974, using the expanding photosphere method, treated 2Ps as a homogeneously expanding photosphere that emits light as a black body. Diluted from atmospheric scattering. This method relies on both the photometry and spectroscopy, where the observed flux is compared to the effective black body flux in the supernova rest frame during the photospheric expansion phase of the supernova 2P. Utilizing the models for the dilution correction factor, the expanded photosphere method, and it looks like I noticed that they expand the meaning of it before. All right, so it's like in a new page they expand the meaning again to make sure we're aware of what they're talking about. I did forget myself. The EPM technique has been applied to numerous Type 2P supernovas from independent samples. A close variant based on the correction of luminosity. A close variant based on the correlations of luminosity with the expansion velocity at 50 days after explosion was suggested and used as a standardized candle method. Okay? For the standardized candle method, luminosity with velocity at 50 days. And that's, sensible because my understanding is they don't often, catch the supernova through its whole explosion. We notice it after it's exploded. We have to extrapolate somehow when it started to expand. And we could extrapolate to 50 days and then standardize from there since we don't have the initial explosion time or data. The method has been further generalized to all epochs in the photospheric phase of the events. A newer technique called the photospheric magnitude method is based on empirical color-based calibration for the distance. Rodriguez et al. Utilized the photospheric magnitude method technique in the near-infrared band where the effects from the dust in line of contamination are much smaller compared to optical wavelengths. Okay. So the idea is that, and we covered this in my stellar astronomy class, there's something called extinction, where as light is going through space, there's dust and debris and hydrogen clouds and various things in between here in the object, even though we may not see it or determine it very well with our eyes. We can learn from other ways that there's things attenuating the light between us and cosmic objects. And that extinction is how much the light has decreased in brightness because of the things that's in between us and the light. That's not only giving it a sort of reddish color, but also knocking out some of the photons from reaching us. So near infrared, like Dr. Keel was telling me the other day, mostly passes through these regions unfazed, the infrared light. So doing these measurements in infrared can allow us to get a direct line to the amount of luminosity coming from that object more accurately because it's just less extinction going on. And it seems that measurement can be utilized to calibrate the visible light. We can compare the infrared to the visible and see how much the light was within a certain amount of error was extracted from the visible light range by the extinction. Jaeger and all suggested a purely photometric technique called the photometric color method that requires no spectroscopy, unlike previous techniques. It is important to test and improve these methods as we discover more 2Ps at higher redshift. These studies involving limited samples of 2Ps at lower redshift show promising signs of them providing independent and competitive distance estimates. represent a cosmological analysis using distances of 2p that are observed by the Rossi 3 telescopes during the 2004 to 2013 survey period. Okay. Distances are derived using the EPM technique and primarily based only on Rossi photometry and coordinated optical spectroscopy. This paper is organized as follows. Section 2, we describe the photometric and spectroscopic data obtained for our SN2P sample. Section 3 describes the data reduction based on the new improved image differing technique. So 2 describes the data. 2 describes the data reduction based on the new improved image differentiation technique, along with photometric calibration, spectroscopy, and K corrections. In section 4, we summarize the mathematical framework for the, it was the EPM again, expanding photosphere method. Section 5 discusses the photometric and spectroscopic parameters for the expanding photosphere method and establishes the time evolution models. The expanding photosphere method distance measurements are discussed in section 6, and section 7 presents the cosmological analysis and the Hubble diagram for our supernova 2P sample. We present the results and discussion in section 8, and finally our conclusions from the paper in section 9. All right, so what I'll do here, let's jump to the conclusion and see what's going on there. Oh, that. So I'm starting to remember some of the tips that my awesome research professor, Dr. Finkelstein, gave us for reading papers, and often it's not best to go straight through the whole paper front to back. I'll go to the conclusion. That'll give me the gist of what's going on. I've already read the abstract and the introduction, and what this will do is give me a general idea of what's going on. And perhaps if I read more of the paper, it'll help things stick out a bit more. And I may even just go to another paper, because I actually have a dissertation that a person wrote using Rossi to constrain the Hubble constant available as well to switch to. Conclusion, we perform an end-to-end analysis. So that means from the beginning to end, we utilize fresh data, the analysis, and so on and so forth. We performed an end-to-end analysis of the time evolution of 2P properties and of the measurement of cosmological properties in the expanding photospheric method framework using photometric and spectroscopic observations of a sample of 12 supernovae 2P. We significantly improved the Rossi supernovae photometry sampling and precision with new image differencing for Rossi supernovae images using a kernel convolution technique. Our analysis of supernovae 2P. In our analysis, we have established excellent performance of unfiltered CCD photometry, including in areas crowded by host nuclei, to yield valuable measurements of the supernovae properties and to measure cosmic expansion in the nearby universe. We demonstrated a broad consistency between supernovae 2P and of the time evolution of event ejecta velocities and photometric temperatures. Okay. We demonstrated a broad consistency between supernovae 2P of the time evolution of the event ejecta velocities and photospheric temperatures from the times of peak luminosity throughout most of the plateau among these diverse supernovae. Okay. There's a consistency between how fast this stuff is expanding and how bright it all is. From well-sampled supernovae photometry with precise estimation of explosion epoch, we empirically established time evolution methods to extrapolate the photospheric velocity and temperature from as few as a single photometric and spectroscopic measurement. Okay. Utilizing the expanding photometric method technique, we obtained the luminosity distances for each supernova. Okay. These distances measurements are in good agreement with host distances in the literature. And so, in other words, it's comparable to the distances that other people have found and already published and has been peer reviewed. And the linearity of the EPM diagram suggests the ability of further generalization of this method. Overall, the EPM technique looks promising to pursue cosmological studies for larger data sets, potentially to even higher redshifts. Utilizing two approaches to fitting for the Hubble constant, we've obtained a measurement of HO about 72.9 kilometers per second per megaparsec. We further established that unknown peculiar velocities do not significantly impact this measurement. Results from the MCMC approach also indicate that we have accounted for all appreciable contributions in their certainties to the scatter of points. I don't remember what MCMC is, but maybe that was mentioned in the middle of the paper, which I have not looked at. All right, so I thought it would show me all the different instances of this, but it's not. Okay, here we go. Markov chain Monte Carlo. Man, so they did some work here. Look at some of the images we have up in here. All right. So it looks like you all can see this okay. I'll zoom in. All right. So the top is a high supernova template sub-image, and the survey sub-image middle of the Rossi 2B field. All right. And the difference image using image diff on the right bottom. A slice from the center of the sub-image showing the Galaxy M74 profile, the fit model, and the residual left. Okay. So we have the data in blue, the model in green, and the residual, which I'm not sure what the residual is. For clarity, the same residual in 2D shown in 80 by 80 pixels in the middle, where R is the measure of the fraction of observation variance preserved in the difference image. In the right panel, the pool distribution shows a Gaussian fit, red, yielding a residual, and the theoretical zero mean unit variance standard normal distribution in black. The pool is closer to standard normal, so this is the type of stuff I'll have to end up doing in my PhD. So I'm going to have to learn a whole lot of stuff. Left 1,000 simulated sources superimposed on the data image. Points show injected sources but do not represent the true PSF shape of the simulated objects. Right, performance of image diff. I'm not sure what image diff is. And they mention image diff over here as well. Overall residual mean is 0, yielding no bias with an RMS root mean square. That must mean root mean square. I'm not sure. I'll check that out. Although close to the limiting magnitude, the RMS is 0.1 magnitude. The full distribution is that. So there's this chi-squared. I had to do that on my undergraduate research, so I'm familiar with chi-squared a bit. All right, let's see what's going on here. Top image subtraction of a 280 by 280 pixel sub-image of ROTC TSS 1246 plus 1249 field. A high supernova template image left obtained with stacking 30 past images. A survey image with potential supernova. So this is a stack of images, right? The middle. A survey image with potential supernova at the center. Right, so this may be a supernova right there. And the difference image with image diff using the sum of the Gaussian kernel convolutions of the template image. SN204GK is clearly visible at the center of the difference image. Okay, so that's this right here. I guess that's a difference of light. You can see the supernova in the middle. Bottom, photometric performance using old and new image differencing methods for supernova 2004 GK. The reduced data points are normalized to the Hamdi et al. V-band magnitude shown in blue points. On MJD, to train the eye, the solid line is the Gaussian process regression fit with the field region being the 95% confidence posterior prediction. The rightmost panel shows the residual of old, which is in green, and new blue light curves after subtracting the residual best fit. Okay. The RMS scatters for the green and blue histograms respectively are 0.36 and 0.10 mags, and the pulls on the new image difference yield dispersion of 1.03, which is substantially improved compared to the old differencing, where the pull yields a dispersion of 2.82. So most of this stuff, I don't know what they're saying. So, right, let's see here. A GP regression model, K corrections, gaze since explosion. On the x-axis, top K corrections derived. Right. It's pretty nearby. It seems like a small redshift to me. It seems interesting. A whole page of images. Almost a whole page. Light curves of supernova in the Rossi 2P sample after final photometric reduction and calibration. The Rossi magnitudes are calibrated to A past V band, followed by the SED correction using equation 11, and the execution and the extinction correction, which I spoke about earlier. Supernovae with redshifts of greater than 0.01 also include the additional K correction. A blue dashed line in each plot represents the adopted explosion epoch for the respective event. Wow. And one more. Region of interest is in green. Continuum. The estimation of the velocity of the HB line using the GMM model. I remember what GMM is again. Top left, the spectrum of supernova 2004 GY taken on January 10, 2005. Oh, so we can see the velocities on the x-axis. So the top is the flux, the bottom, the flux versus velocity. Oh, rest wavelengths. Some good stuff. I think I'll go ahead and pause here. And I'll be back. And we'll be back to do some problems and maybe do some reading later. So thanks whoever popped in. Be sure to like, subscribe, comment if you haven't. I'll look for any comments on the comment section of the video. I'll see you all later for sure. Do some problems, do some more reading. I'll see you all then.